close your eyes and imagine floating effortlessly through space, unburdened by weight, drifting as easily as a feather on the wind. You've seen the images: astronauts tumbling gracefully through space stations, water forming perfect spheres in mid-air, objects hanging motionless as if suspended by invisible strings. This is weightlessness, one of the most mesmerizing aspects of spaceflight, yet also one of the most misunderstood. Most people believe that astronauts float because there's no gravity in space. They imagine crossing some invisible boundary where Earth's pull simply stops, where gravity switches off like a light. But this common belief is profoundly wrong. Gravity doesn't disappear in space. It's everywhere, always pulling, always present. The International Space Station, orbiting 250 miles above Earth, experiences gravity only slightly weaker than what we feel on the ground, about 90% of Earth's surface gravity. So why do astronauts float? The answer is both simple and profound. They're falling, constantly, endlessly falling toward Earth, but moving sideways so fast that they keep missing. This state of perpetual free fall creates the sensation we call weightlessness. It's not the absence of gravity, but a perfect balance between falling and moving forward that creates this magical floating sensation. Tonight, we'll explore the nature of gravity and weightlessness, unraveling the physics that governs motion in space. We'll discover why gravity is the universe's most fundamental force, how it shapes everything from falling apples to orbiting galaxies. We'll learn what weightlessness really is and how astronauts experience it. We'll explore whether anti-gravity, gravity's mysterious opposite, could exist, and what science says about manipulating gravity itself. This is a journey into one of nature's deepest mysteries, a force so fundamental that it literally holds the universe together, yet so subtle that we still don't fully understand how it works. It's a story of falling bodies and orbiting worlds, of Einstein's genius and the limits of human knowledge, of the difference between what we feel and what is real. So settle in, take a deep breath, and prepare to see gravity with new eyes. The force you've lived with every moment of your life is stranger and more wonderful than you ever imagined. Gravity is the universe's most familiar force, yet also its most mysterious. We experience it every moment: the weight of our bodies, the fall of dropped objects, the arc of a thrown ball. Yet despite centuries of study, gravity remains the least understood of nature's fundamental forces. We know what it does. We can predict its effects with extraordinary precision, but we still don't fully know what it is or why it exists. For most of human history, gravity wasn't even recognized as a force. Objects fell because they sought their natural place. Heavy things belonged down, light things belonged up. The earth was the center of everything, and celestial bodies moved in perfect circles because circles were divine. This Aristotelian view dominated Western thought for 2 millennia, despite its many contradictions and failures to match observation. Isaac Newton changed everything. In the 1680s, Newton published his law of universal gravitation, proposing that every object with mass attracts every other object with mass. The force between them depends on their masses and the distance separating them. Double the mass, double the force, double the distance, reduce the force to 1/4. This simple inverse square law explained falling apples and orbiting moons with the same mathematics. It unified terrestrial and celestial physics, showing that the same force governing Earth governed the heavens. Newton's law was revolutionary because it was universal. Gravity wasn't different things acting on different objects. It was one force, following one rule, acting on everything, everywhere, always. An apple falls to Earth with the same force law that keeps the moon in orbit. Jupiter's gravity holds its moons for the same reason Earth's gravity holds us. The mathematics is identical, only the numbers change. Newton's gravity is a force acting at a distance. Somehow, Earth reaches across empty space and pulls on the moon. The Sun reaches across 93 million miles and pulls on Earth. This action at a distance bothered Newton himself. He admitted he couldn't explain the mechanism, only describe the effects. But the law worked so perfectly that it became the foundation of physics for 2 centuries. Astronomers used it to predict planetary motions, discover new planets, and map the solar system with extraordinary precision. But Newton's gravity had subtle problems. It predicted instant transmission. If the Sun suddenly vanished, Earth would immediately fly off in a straight line, feeling the absence of gravity at once. This instantaneous action violated emerging understanding about the finite speed of light and information. And Newton's gravity failed in extreme conditions. Mercury's orbit precessed drifted slightly more than Newton's law predicted. The discrepancy was tiny but real and unexplained. Enter Albert Einstein. In 1915, Einstein published his general theory of relativity, completely reimagining gravity. In Einstein's view, gravity isn't a force pulling objects together. It's the curvature of space-time itself. Mass and energy warp the fabric of space and time around them, creating curves and valleys in the geometry of the universe. Objects moving through curved space-time follow curved paths, which we interpret as gravitational attraction. Imagine a bowling ball placed on a trampoline. The ball creates a depression, curving the trampoline's surface. If you roll a marble near the bowling ball, it curves toward the ball, not because the ball pulls it, but because the marble follows the curved surface of the trampoline. This is Einstein's gravity, not a force reaching across space, but a consequence of moving through curved space. General relativity resolved Newton's problems. It predicted that gravity propagates at the speed of light, not instantly. It explained Mercury's orbital precession perfectly. It predicted new phenomena, that light bends near massive objects, that time runs slower in strong gravitational fields, that sufficiently massive objects can collapse into black holes from which not even light escapes. Every prediction has been confirmed by observation. Yet, even Einstein's gravity is incomplete. It's incompatible with quantum mechanics, our other great theory of nature. At the smallest scales inside atoms, near the Big Bang, at the centers of black holes, general relativity breaks down. We don't know how to reconcile gravity with quantum physics. The search for a quantum theory of gravity, a theory unifying all forces and explaining gravity at the deepest level, remains one of physics's greatest challenges. Despite our incomplete understanding, we know gravity's effects intimately. Gravity is always attractive. It only pulls, never pushes. Unlike electromagnetism, which can attract or repel depending on charges, gravity has one sign. Every mass attracts every other mass. This universal attraction is why gravity dominates at large scales. Individual atoms barely affect each other gravitationally, but collect enough atoms into a planet or star, and gravity becomes overwhelming. Gravity is also the weakest fundamental force by far. The electromagnetic force between two electrons is about 10^42 times stronger than the gravitational force between them. A small magnet can pick up a paperclip, overcoming the gravitational pull of the entire Earth. Yet gravity wins at cosmic scales because it's cumulative and always attractive. Electromagnetic forces cancel as positive and negative charges balance. Gravity just keeps adding up. This weakness makes gravity hard to study in laboratories. We can't shield from gravity or create anti-gravity. We can measure it with extraordinary precision. Modern instruments detect gravitational waves from colliding black holes billions of light years away, but we can't manipulate it. Every attempt to control gravity requires moving mass around, which requires enormous energy. This is why, despite science fiction's dreams, we have no gravity generators, no tractor beams, no anti-gravity propulsion. Understanding what gravity is requires accepting that it's profoundly different from our intuitions. It's not a force in the traditional sense. It's the shape of space-time itself, the geometry of the universe responding to the presence of mass and energy. When you feel weight, you're not feeling gravity pulling you down. You're feeling the ground pushing you up, preventing you from following your natural path through curved space-time, a path that would be free fall. We use the words weight and mass interchangeably in everyday language, but they're fundamentally different concepts. Understanding this difference is key to understanding weightlessness. Mass is the amount of matter in an object, how much stuff it contains. Mass is intrinsic to the object, the same everywhere in the universe. A kilogram of iron contains the same number of atoms, whether it's on Earth, on the Moon, or floating in deep space. Mass determines how hard it is to accelerate an object its inertia. Push a boulder and a pebble with the same force. The pebble accelerates much more because it has less mass. Weight, by contrast, is the force exerted on an object by gravity. Weight depends on both the object's mass and the strength of the local gravitational field. On Earth's surface, a kilogram of iron weighs about 2.2 pounds, or more precisely, experiences a force of 9.8 newtons. On the Moon, where gravity is 1/6 as strong, the same kilogram weighs only 0.37 pounds. In deep space, far from any massive body, it weighs essentially nothing, though its mass remains 1 kilogram. This is the critical insight. Mass never changes, but weight does. An astronaut floating in the International Space Station hasn't lost mass. They still contain the same atoms, bones, muscles, and organs. But they've lost weight because they're in free fall. Here's the key to understanding weightlessness. Weight is what you feel when something prevents you from falling freely under gravity's influence. Right now, as you read this, you're experiencing weight because the ground or chair or bed is pushing up on you, preventing you from falling toward Earth's center. This upward force from the ground creates the sensation of weight. Remove that force, step off a diving board, jump from a plane, orbit the Earth, and you become weightless, even though gravity is still acting on you. This seems paradoxical. How can gravity be pulling on you while you feel weightless? The answer lies in what you actually feel. You don't directly feel gravity. You feel the resistance to gravity, the forces that prevent you from falling freely. When you stand, you feel your bones compressing under the load, your muscles working to maintain posture, the pressure of the ground on your feet. When these sensations vanish, you feel weightless, regardless of whether gravity is present. The International Space Station orbits Earth at an altitude of about 250 miles. At that altitude, Earth's gravitational pull is still about 90% as strong as at the surface. If you could somehow place a scale at ISS altitude and stand on it, supported by something other than orbital motion, you'd weigh nearly as much as on the ground. But astronauts aboard ISS don't stand on scales. They orbit, moving at about 17,500 miles per hour, and everything inside crew, equipment, air falls toward Earth together. This is the essence of orbital weightlessness. It's not zero gravity, but zero apparent weight due to continuous free fall. The station is falling toward Earth, but moving forward so fast that Earth's surface curves away beneath it at the same rate. The station continuously falls around Earth, never getting closer or farther away. Everything inside falls at the same rate, so nothing pushes on anything else. Without forces between objects, there's no sensation of weight. You can experience brief weightlessness on Earth. Ride an elevator and notice the momentary lightness when it starts descending, or the heaviness when it starts ascending. In the moment of free fall, downward acceleration, you become slightly lighter. Jump off a diving board and you're completely weightless during the fall until air resistance builds up and you hit the water. Astronaut training includes flights on specially designed aircraft that follow parabolic paths, creating 20 to 30 seconds of weightlessness at the top of each parabola. These vomit-comet flights let astronauts practice working in weightlessness without leaving Earth. The physics of free fall is elegant. When an object falls freely under gravity alone, with no air resistance or other forces, every part of it falls at the same rate regardless of mass. A hammer and a feather, dropped simultaneously on the airless moon, hit the ground at the same instant as Apollo 15 Commander David Scott famously demonstrated. This is called the equivalence principle. Gravitational mass, how strongly gravity pulls on an object, equals inertial mass, how hard it is to accelerate that object. Because these are equal, all objects fall at the same rate. This equivalence is not obvious. There's no reason in Newtonian physics why gravitational mass must equal inertial mass. They're defined differently and measured differently. Yet experiments confirm they're equal to at least 1 part in a trillion. Einstein built general relativity on this equivalence, recognizing it as a profound clue about gravity's nature. The equivalence principle leads to a startling conclusion. You can't tell the difference between being in a gravitational field and being in an accelerating reference frame. Stand in an elevator on Earth. You feel weight, Now imagine the elevator in deep space, far from any gravity, but accelerating upward at 9.8 meters per second squared, Earth's surface gravity. You'd feel the same weight. Everything dropped would fall to the floor at the same rate, really. The floor is accelerating up toward it. You couldn't tell whether you're in a gravitational field or an accelerating spaceship. Similarly, float freely in space and you can't tell whether you're in deep space, true zero gravity, or orbiting Earth freefall in strong gravity. Both feel weightless. This is why astronauts describe the sensation as floating rather than zero gravity. The sensation is the same whether gravity is present or not. Weightlessness has profound effects on the human body, most of them negative. On Earth, your bones and muscles constantly work against gravity. Blood pools in your legs, your heart pumps it upward against gravity. In weightlessness, these systems become unnecessary. Bones lose density about 1 to 2% per month in orbit. Muscles atrophy. Fluids shift upward, causing puffy faces and thin legs. The heart weakens. The immune system changes. Vision problems develop. These changes make long-duration spaceflight challenging and limit how long humans can safely remain in space without countermeasures. Astronauts exercise for hours daily to combat these effects, using resistance devices and treadmills that strap them down. But exercise only partially compensates. After 6 months in space, astronauts return to Earth weakened, requiring weeks or months to fully recover. For missions to Mars involving years in space, managing the health effects of prolonged weightlessness is one of the biggest challenges. The experience of weightlessness is disorienting at first. Your inner ear, which senses gravity and acceleration, provides conflicting signals. About half of astronauts experience space adaptation syndrome, nausea, disorientation, vomiting during the first few days. The brain adjusts, usually within 2 to 3 days, learning to ignore the confusing signals. But returning to Earth reverses the adaptation, causing similar symptoms until the brain readjusts to gravity. Despite the challenges, astronauts often describe weightlessness as exhilarating. Movement becomes effortless. You can orient yourself any direction, there's no up or down. You can lift massive objects with a finger's push. You can somersault, tumble, soar across a room with the slightest push. It's the closest humans have come to flying. Many astronauts say that despite the hardships of space, they miss the sensation of floating. To understand weightlessness in space, we must understand orbits. An orbit is not a place where gravity stops. It's a specific speed at a specific altitude where you fall toward a body at exactly the rate needed to keep missing it. Understanding this transforms how we think about space stations, satellites, and spacecraft. Imagine standing on a mountain and throwing a ball horizontally. The ball follows a curved path, falling toward Earth while moving forward, eventually hitting the ground some distance away. Throw it harder, and it goes farther before landing. The ball's trajectory is always curved toward Earth, pulled by gravity, but the faster you throw it, the farther it goes. Now imagine throwing the ball so fast that Earth's surface curves away beneath it as fast as the ball falls toward it. The ball would never hit the ground, it would be in orbit, continuously falling but never getting closer. This is the essence of orbital motion. An orbiting object is in perpetual free fall, but moving sideways fast enough that the ground falls away at the same rate. For Earth orbit, at the ISS's altitude of 250 miles, this speed is about 17,500 miles per hour. Slower than this, and you fall to Earth. Faster, and you move into a higher orbit, or escape Earth entirely. This specific speed isn't arbitrary, it's determined by Earth's mass and the orbital altitude. More massive planets require higher orbital speeds. Higher altitudes require lower speeds because gravity weakens with distance. Isaac Newton grasped this concept in the 1680s, illustrated by his Newton's cannonball thought experiment. Imagine a cannon on a mountaintop firing a cannonball horizontally. At low speeds, the cannonball hits Earth nearby. At higher speeds, it lands farther away. At a specific speed orbital velocity, the cannonball falls around Earth continuously, never landing. Fire faster still, and the cannonball escapes Earth entirely, heading into deep space. This thought experiment revealed that orbital motion and falling to Earth are the same thing. The Moon orbits Earth not because it's immune to gravity, but because it's falling toward Earth while moving sideways fast enough to keep missing. The planets orbit the Sun the same way, continuous freefall, perfectly balanced by forward motion. Orbits come in different shapes and sizes. The simplest is a circular orbit, where the object maintains constant altitude and speed. Circular orbits are stable and easy to maintain. The ISS orbits in a nearly circular orbit, completing one lap around Earth every 90 minutes. GPS satellites orbit at about 12,500 miles altitude in circular orbits, completing 2 orbits per day. Geostationary satellites orbit at 22,236 miles altitude, completing 1 orbit in 24 hours, matching Earth's rotation rate, so they appear stationary above a point on the equator. Elliptical orbits are stretched circles. The orbiting object alternately approaches and recedes from the body it orbits, speeding up when closer and slowing when farther away. Most natural orbits are elliptical. Planets orbit the Sun in ellipses, though nearly circular for most planets. Comets have extremely elliptical orbits, swooping close to the Sun then retreating to the outer solar system. Johannes Kepler discovered the laws governing orbits in the early 1600s, before Newton explained why they worked. Kepler's laws describe how planets move. Orbits are ellipses with the Sun at one focus. A line from the Sun to a planet sweeps out equal areas in equal times, meaning planets move faster when closer to the Sun. The square of the orbital period equals the cube of the semi-major axis, a relationship connecting orbital size to orbital period. These laws, derived from careful observation of Mars, applied to all planets and moons. Newton later showed they were consequences of his law of universal gravitation. The energy of an orbit determines its size. Add energy, speed up, and the orbit becomes larger and more elliptical. Remove energy, slow down, and the orbit shrinks. At a specific energy, the escape velocity, the orbit becomes an open path, parabola or hyperbola, that doesn't return. The object escapes the gravitational system entirely. For Earth's surface, Escape velocity is about 25,000 miles per hour. The Apollo missions to the Moon had to reach this speed to break free of Earth's gravity. Changing orbits requires energy. To go from a low orbit to a high orbit, you must speed up, adding energy. This seems counterintuitive because objects in higher orbits actually move slower than objects in lower orbits. But the process of moving to a higher orbit involves speeding up at the low point, which raises the orbit's high point. Once in the higher orbit, you slow down to circularize it. The total energy is higher, even though the circular velocity is lower. This is why spaceflight is hard. Reaching orbit requires enormous speeds. Orbital velocity around Earth is about 17,500 miles per hour. Escaping Earth requires 25,000 miles per hour. Going to Mars requires first escaping Earth, then changing your orbit around the Sun to intersect Mars's orbit. Every maneuver requires propellant, and propellant is heavy. Most of a rocket's mass is fuel, used just to lift more fuel, in a vicious cycle that makes spaceflight expensive and challenging. Gravity assists, discussed in previous chapters, help by stealing energy from planets. Flying close to a planet, a spacecraft can use the planet's motion to gain speed without using propellant. This makes missions to the outer solar system feasible with existing rockets. Orbits are stable if nothing disturbs them, but perfect stability is rare. In low Earth orbit, traces of atmosphere create drag, gradually slowing spacecraft and lowering their orbits. Without periodic boosts, everything in low orbit eventually falls to Earth. The ISS requires regular reboosts using engines on cargo spacecraft to maintain altitude. Higher orbits above the atmosphere can remain stable for millions of years. Natural satellites like the Moon are in stable orbits, refined over billions of years. The Moon's orbit is nearly circular, though tidal interactions slowly push it farther from Earth, about 1.5 inches per year. In hundreds of millions of years, the Moon will be significantly farther away, orbiting more slowly. Understanding orbits clarifies why astronauts float. They're not in a special place where gravity stops. They're in continuous free fall, and everything around them falls together. The space station is a shared free fall environment. Inside, everyone and everything experiences weightlessness because nothing pushes on anything else. It's the same sensation you'd feel in an elevator with a cut cable, except the elevator would eventually hit the ground while the space station falls forever around and around Earth. The term zero gravity or zero G is common but misleading. Astronauts aboard the ISS don't experience zero gravity, they experience microgravity, a subtle but important distinction. Microgravity refers to the very small gravitational effects that remain even in orbit. The ISS is large, over 350 feet long. Earth's gravity is slightly stronger on the side facing Earth than on the side facing away, because gravity weakens with distance. This difference creates a slight tidal force trying to stretch the station. For objects inside the ISS, these tidal forces are tiny, on the order of a millionth of Earth's surface gravity, hence microgravity. A floating astronaut experiences nearly perfect weightlessness, but ultra-sensitive instruments can detect residual forces. For most purposes, the environment is effectively weightless, but for precision experiments, growing protein crystals, studying fluid dynamics, testing fundamental physics, microgravity effects matter. Other sources of microgravity include atmospheric drag. Yes, there's still trace atmosphere at ISS altitude, solar radiation pressure, and vibrations from equipment and crew movement. These forces are minute but non-zero. Spacecraft designers must account for them in precision experiments. The ISS itself is designed to minimize microgravity disturbances for experiments. Certain modules are designated quiet zones where crew activity is restricted during sensitive experiments. Equipment that vibrates treadmills, life support pumps, is mounted on isolation systems to reduce transmitted vibrations. Some experiments require even better microgravity than the ISS provides. For these, scientists use drop towers, tall shafts, where experimental packages are dropped, providing a few seconds of high-quality microgravity. The best drop towers create microgravity environments 10,000 times better than the ISS, truly approaching 0G, but only for 5 to 10 seconds. Sounding rockets provide another option. These suborbital rockets follow ballistic trajectories, reaching space and falling back to Earth. At the peak of their arc, they experience several minutes of microgravity, better than drop towers, but not as good as orbit. Sounding rockets are cheaper than orbital missions and can provide sufficient microgravity for many experiments. For truly long-duration microgravity, orbit is the only option. The ISS National Laboratory hosts hundreds of experiments, taking advantage of the unique environment. Experiments study protein crystal growth for drug development. Combustion physics, flames behave very differently without convection. Fluid dynamics, materials science, plant growth, and human physiology. Microgravity affects physics in surprising ways. On Earth, convection, warm fluid rising, cool fluid sinking dominates many processes. In microgravity, convection vanishes. Candle flames become spherical instead of teardrop-shaped, burning in a shell around the wick. Boiling water doesn't bubble, normally vapor forms large blobs that hover in the liquid. Mixing fluids becomes difficult without gravity to drive flow. These differences make microgravity valuable for science. Processes masked by gravity on Earth become visible in orbit. Materials can be studied in pure states, impossible to maintain on Earth. Protein crystals grow larger and more perfect, revealing structures important for drug design. Alloys can be mixed that would separate in Earth's gravity. Microgravity also poses challenges. Eating and drinking require special techniques and packaging. Liquids don't pour, they form blobs that float away. Crumbs don't fall harmlessly to the floor, they float around, potentially clogging filters or getting in eyes. Bathrooms require airflow to direct waste into containment. Sleeping requires strapping down or you drift around the cabin. Exercise equipment must strap the user down. The human body in microgravity undergoes numerous changes. Blood pressure equalizes, no longer working against gravity to pump blood upward. This causes fluid shifts toward the head, resulting in puffy faces and stuffy sinuses. The spine extends as vertebrae separate slightly, making astronauts taller 1 to 2 inches. Bones demineralize, particularly in load-bearing structures like legs and hips. Muscles atrophy without resistance training. The heart becomes slightly weaker. Vision problems are particularly concerning. Many astronauts develop changes in eye shape and vision during long missions. The exact mechanism is unclear, but likely involves fluid pressure changes affecting the eye and optic nerve. Some vision changes persist after returning to Earth, a worrisome finding for long-duration missions like trips to Mars. Immune system function changes in microgravity. Some immune responses weaken, others become overactive. Wound healing slows. Bacteria and viruses behave differently. These changes aren't fully understood, but could pose risks for long missions far from Earth's immediate medical support. Radiation exposure increases in space. Earth's atmosphere and magnetic field protect surface dwellers from cosmic rays and solar radiation. In orbit, only the spacecraft hull provides shielding. The ISS orbit stays within Earth's magnetic field, providing some protection, but astronauts receive about 150 to 200 millisieverts per year, about 50 times the annual dose for people on Earth. On missions beyond Earth's magnetic field, like trips to the Moon or Mars, radiation exposure would be much higher. Despite challenges, humans adapt remarkably well to microgravity. After initial space sickness, most astronauts function effectively. They report that movement becomes intuitive. After a few days, their brains adapt to the new environment. Many say they prefer the freedom of three-dimensional movement to Earth's rigid, floor-oriented existence. Some physiological changes might be beneficial. Heart patients could benefit from reduced cardiac workload. Studies of aging in space reveal accelerated versions of processes that occur slowly on Earth, providing insights into mechanisms and potential treatments. Microgravity manufacturing might enable products impossible to make on Earth: perfect spheres, exotic alloys, ultra-pure crystals. For future space exploration, managing microgravity's effects is crucial. Missions to Mars will involve months of travel in microgravity, followed by arrival at a planet with only 38% of Earth's gravity, then months of microgravity returning home. Astronauts must remain healthy and capable throughout. Countermeasures, exercise, drugs, possibly artificial gravity will be essential. Some propose generating artificial gravity on spacecraft using rotation. A rotating spacecraft creates centrifugal force that simulates gravity. The crew experiences a push toward the hull, creating a sensation similar to weight. This requires either a very large spacecraft or rapid rotation. The Hermes spacecraft in The Martian used rotation to create artificial gravity, scientifically plausible, though engineering such a spacecraft is beyond current capabilities. For now, astronauts live and work in microgravity, experiencing the closest thing to true weightlessness humans have achieved. It's not perfect zero-G, but close enough to provide the sensation of floating, the freedom of three-dimensional movement, and the scientific opportunities of a gravity-free environment. Science fiction is full of anti-gravity devices that cancel or reverse gravity, allowing starships to hover effortlessly and accelerate without rockets. But does anti-gravity exist in reality? Can gravity be blocked, reversed, or manipulated? The answers are complex and surprising. First, let's clarify what anti-gravity might mean. It could mean 1. A force that opposes gravity, pushing objects apart instead of pulling together. 2. A way to block or shield from gravity. 3. A way to generate controllable gravitational fields. Each has different scientific status. In Newton's physics, anti-gravity seems impossible. Gravity is always attractive, pulling masses together. There's no negative mass that would repel. You can't shield from gravity, no material blocks gravitational fields. Unlike electromagnetism, where opposites attract and likes repel, and where metal shields block fields, gravity has only one sign and penetrates everything. Einstein's general relativity offers slightly more possibilities. In GR, gravity is space-time curvature caused by mass and energy. Anything with positive mass or energy curves space-time in ways that attract other masses. But what about negative mass or energy? Negative mass is hypothetical. If it existed, it would have bizarre properties. Negative mass would have negative weight, it would fall up, not down. Push on negative mass, and it would accelerate toward you, not away. Negative and positive masses would chase each other forever, in an absurd perpetual motion. No evidence suggests negative mass exists, and most physicists believe it's impossible it would violate energy conservation and causality. Negative energy, however, might exist in limited forms. Quantum field theory allows for negative energy density in certain situations. The Casimir effect, where two metal plates placed very close together experience a small attractive force due to negative energy between them. Some solutions to Einstein's equations, like wormholes and warp drives, require negative energy to remain stable. But these are exotic quantum effects, not macroscopic anti-gravity. Could we shield from gravity? In general relativity, not really. Gravity curves space-time itself. You can't interpose something that blocks curvature. The curvature is the shape of space. However, you can imagine surrounding yourself with a massive shell. Inside a perfectly spherical shell of matter, gravitational forces from all directions cancel out, creating zero net gravitational force. This is the shell theorem, known since Newton. But this isn't really shielding. The gravity from the shell cancels itself, and you'd still feel gravity from any masses outside the shell. More speculatively, some theories suggest gravity might be manipulated by controlling space-time geometry directly. If you could create specific distributions of matter and energy or exotic forms like negative energy, you might warp space-time in useful ways. The Alcubierre warp drive, a theoretical solution to Einstein's equations proposed in 1994, describes a bubble of contracted space in front of a spacecraft and expanded space behind, effectively moving the spacecraft faster than light without accelerating it through space. But this requires negative energy in amounts that might be physically impossible and may violate causality. What about electromagnetic levitation? Is that anti-gravity? Not really. Magnetic levitation, maglev, uses electromagnetic forces to counteract gravity, holding objects suspended. This is real and practical. Maglev trains levitate above tracks using powerful magnets. But this isn't anti-gravity. It's a different force, electromagnetism, pushing upward with enough strength to counter gravity's downward pull. The gravity is still there, unchanged. It's like holding a ball in your hand. You're not creating anti-gravity, just exerting a force that counteracts gravity. Some proposals involve spinning massive objects. The Lense-Thering effect, a prediction of general relativity, says that rotating masses drag spacetime around them slightly. Near a spinning black hole, this frame dragging becomes extreme. Some have speculated whether spinning massive disks could generate useful gravitational effects, perhaps even anti-gravity-like forces. But calculations show the effects are incredibly tiny for any feasible device. You'd need something as massive and dense as a neutron star, spinning at a significant fraction of light speed, to create measurable frame dragging. Not practical. In 1996, Russian scientist Eugene Podkletnov claimed to have discovered gravitational shielding using a spinning superconducting disk. Objects above the disk supposedly weighed slightly less. If true, this would revolutionize physics, but the effect couldn't be reproduced by other researchers. Most physicists believe it was experimental error or fraud. No validated evidence for gravitational shielding exists. Various anti-gravity devices have been proposed over the years. None work. Dean drives, lifters, spinning gyroscopes that supposedly reduce weight all fail under careful testing. What looks like anti-gravity is usually misunderstood aerodynamics, electromagnetic forces, or experimental error. The laws of physics, as currently understood, don't allow for controllable anti-gravity. However, there's one intriguing possibility: dark energy. Observations since the 1990s show the universe's expansion is accelerating. Something is pushing space apart, counteracting gravity's inward pull on cosmic scales. We call this dark energy, but we don't know what it is. It acts like anti-gravity on scales of millions of light years, not pulling masses together, but pushing space apart. Dark energy makes up about 68% of the universe's total energy, yet it's extraordinarily diffuse and weak on small scales. Its effects are only noticeable across vast distances. We have no idea how to harness or control dark energy. It may be a property of space itself, cosmological constant, or a dynamic field that evolves over time, quintessence. Understanding dark energy is one of cosmology's biggest challenges. So, does anti-gravity exist? In the sense of a force or technology that opposes gravity in practical, controllable ways, no. Gravity is always attractive, always present, and can't be blocked or reversed with any known physics. Science fiction's anti-gravity drives, tractor beams, and gravity generators remain fantasy. But nature is full of surprises. Decades ago, dark energy was unsuspected. Quantum mechanics revealed phenomena Newton couldn't have imagined. Future discoveries might reveal aspects of gravity we don't currently understand. Perhaps quantum gravity, when finally understood, will offer insights or possibilities currently unimaginable. For now, if we want to oppose gravity, we use other forces. Thrust from rockets, lift from wings, electromagnetic repulsion from magnets. These aren't anti-gravity, but they work. They're how we fly, how we reach orbit, how we escape Earth's pull, not as elegant as science fiction's gravity generators, but real, proven, and sufficient to take us into space. While we experience gravity as a gentle, constant pull toward Earth's center, gravity can manifest in extreme forms that defy everyday intuition. At the heart of massive stars and in the depths of black holes, gravity becomes so intense that it dominates all other forces, crushing matter into exotic states and bending space-time into bizarre geometries. On Earth's surface, gravity accelerates objects at 9.8 meters per second squared. This is comfortable for human life, strong enough to keep us grounded, but weak enough that we can move freely. Other bodies in the solar system have different surface gravities. The Moon's gravity is about 1/6 Earth's, enough to keep astronauts on the surface, but weak enough to allow dramatic leaping. Mars has about 38% of Earth's gravity. Jupiter, massive though it is, has only 2.5 times Earth's surface gravity because its radius is so large. The Sun, despite being 333,000 times more massive than Earth, has only 28 times Earth's surface gravity. But compact objects generate extreme gravity. A white dwarf, the collapsed core of a dead sun-like star, about Earth's size, but with the Sun's mass, has surface gravity about 350,000 times Earth's. Matter on a white dwarf's surface weighs hundreds of thousands of times more than on Earth. Nothing familiar could exist there. The extreme gravity crushes atoms, stripping electrons from nuclei and packing matter to densities of tons per teaspoon. Neutron stars are more extreme. When a massive star explodes as a supernova, its core collapses beyond white dwarf density into a ball of neutrons about 12 miles in diameter, but 1.4 to 2 times the Sun's mass. Surface gravity on a neutron star is about 200 billion times Earth's. The escape velocity is about 1/3 the speed of light. Matter is compressed to nuclear density. A teaspoon of neutron star material weighs about 1 billion tons. Mountains on neutron stars are millimeters high, instantly flattened by extreme gravity. At these densities, matter behaves in ways impossible to recreate in laboratories. Atomic nuclei touch each other, forming a continuous nuclear fluid. Protons and electrons are crushed together, forming neutrons. Deeper still, neutrons might dissolve into quarks. The exact state of matter at a neutron star's core is unknown. Experiments can't reach such conditions, and theory is uncertain. Black holes are the ultimate expression of gravity. When matter is compressed enough, space-time curves so severely that even light cannot escape. The boundary of no return is the event horizon. Cross it, and you can never come back. Nothing, not even light traveling at the universe's ultimate speed, can fight the gravity inside a black hole's event horizon. The event horizon's size depends on the black hole's mass. For a black hole with the Sun's mass, the event horizon would be about 3 miles in radius. For a supermassive black hole at a galaxy's center with billions of solar masses, the event horizon can span billions of miles larger than our solar system. Near a black hole's event horizon, gravity's tidal forces become severe. If you fell feet first toward a stellar mass black hole, the gravity at your feet would be enormously stronger than at your head, just a few feet farther away. This tidal force would stretch you, squeezing your sides while pulling your head and feet apart, a process colorfully termed spaghettification. Long before reaching the event horizon, you'd be torn apart by tidal forces. For supermassive black holes, the event horizon is so large that tidal forces at the horizon are mild. You could cross the event horizon of a billion solar mass black hole without even noticing the moment of crossing. Only later, when you tried to return and discovered you couldn't, would you realize you'd crossed the point of no return. Inside a black hole, general relativity predicts a singularity, a point of infinite density and curvature where the laws of physics break down. All matter that falls into a black hole eventually reaches the singularity, where it's crushed to infinite density. What happens at the singularity is unknown. General relativity predicts it, but also breaks down there, unable to describe what happens when density becomes infinite. Quantum gravity, when developed, may resolve the singularity, replacing it with something less pathological. But for now, the center of a black hole remains a profound mystery. Black holes warp time as well as space. Near the event horizon, time slows dramatically relative to distant observers. An observer far from the black hole watching something fall in would see the falling object slow as it approached the horizon, taking infinite time to actually cross from the distant observer's perspective. The falling object's clock runs slower and slower, freezing at the horizon. From the falling object's perspective, however, time passes normally. You'd cross the horizon in finite time on your watch, seeing the universe outside speed up and eventually watching the distant future unfold in moments as you fell toward the singularity. This time, dilation is real and measurable. Atomic clocks near massive objects run slower than identical clocks farther away. GPS satellites must account for this effect. Their clocks run slightly faster than ground-based clocks because they're farther from Earth's gravitational field. Without correcting for relativistic time dilation, GPS would accumulate errors of miles per day. Gravity waves, ripples in space-time itself, are produced by accelerating masses, much as electromagnetic waves are produced by accelerating charges. But gravity waves are incredibly weak. Only the most violent events, colliding black holes, merging neutron stars, supernova explosions, generate detectable gravity waves. The Laser Interferometer Gravitational Wave Observatory, LIGO, detected the first gravity waves in 2015 from two black holes merging over 1 billion light-years away. The waves changed distances on Earth by a fraction of a proton's diameter, yet LIGO's exquisitely sensitive detectors measured them. Gravity wave astronomy is revealing a new side of the universe. Colliding black holes, previously theoretical, are now observed regularly. The 2017 detection of merging neutron stars, observed in both gravity waves and light, revealed that neutron star collisions forge heavy elements like gold and platinum. Gravity waves will let us observe events impossible to see with light, the Big Bang's first moments, black holes merging in obscuring dust, even dark matter interactions if they generate waves. At extremes, gravity reveals its strange relationship with entropy and information. Black holes have entropy proportional to their event horizon area, not volume, a relationship that baffled physicists and hints at deep connections between gravity, thermodynamics, and information. Stephen Hawking showed that quantum effects cause black holes to slowly evaporate, emitting radiation and eventually disappearing. This raises paradoxes. Does information that falls into a black hole get destroyed, violating quantum mechanics? Resolving these questions may require a quantum theory of gravity. Studying gravity at extremes tests our theories in regimes far beyond everyday experience. General relativity predicts all these phenomena: time dilation, event horizons, singularities, gravity waves, and observations keep confirming its predictions. Yet we know GR is incomplete. It doesn't incorporate quantum mechanics. At the Planck scale, distances around 10⁻35 meters, quantum effects and gravity become equally important, and neither theory works. Understanding gravity at these extremes may require revolutionizing physics as profoundly as Einstein revolutionized Newton's physics a century ago. For humans to thrive during long-duration spaceflight missions to Mars, asteroid mining, space stations for thousands, we may need artificial gravity. Months or years in microgravity damage health in ways exercise can only partially address. Creating artificial gravity could solve these problems, but doing so presents formidable engineering challenges. The only proven method for creating sustained artificial gravity is rotation. A rotating spacecraft experiences centrifugal force, not a true force, but the sensation objects feel when moving in a circle. Stand in a rotating spacecraft, and you're constantly accelerating toward the center to maintain circular motion. Your feet push against the hull, which pushes back, creating a sensation indistinguishable from gravity. The centrifugal force depends on rotation rate and radius. Spin faster or make the radius larger, and the force increases. For a spacecraft to generate Earth normal gravity 1 gram, the rotation rate depends on its size. A small capsule would need to spin very fast, uncomfortably fast, creating disorienting Coriolis effects. A large structure, a rotating wheel kilometers in diameter, could spin slowly and comfortably. The Coriolis effect is the biggest challenge. In a rotating frame, moving objects appear to deflect sideways. Throw a ball forward and it curves. Walk spinward and you feel lighter. Walk anti-spinward and you feel heavier. Turn your head quickly and you feel dizzy as your inner ear signals conflict with your vision. These effects are stronger for faster rotation and smaller radius. Studies suggest humans can adapt to rotation rates up to about 4 revolutions per minute without severe discomfort, though 2 revolutions per minute is preferred. At 4 revolutions per minute, generating 1 gram requires a radius of about 56 meters. At 2 revolutions per minute, you need 224 meters. This means a spacecraft must be quite large, hundreds of meters in diameter, to comfortably generate Earth gravity through rotation. No spacecraft with artificial gravity has been built, though designs exist. The most famous is the Stanford Torus, a 1970s design for a rotating space station housing 10,000 people. Shaped like a giant donut, 1.8 kilometers in diameter, rotating once per minute, it would generate Earth gravity in the outer rim while maintaining a microgravity hub. The design is practical but expensive, requiring millions of tons of material launched to orbit beyond current capabilities. Smaller rotating designs are more feasible. A crewed Mars mission might use two spacecraft tethered together, rotating around their common center. This requires no massive structure, just a tether and small thrusters for spin-up. The astronauts experience artificial gravity, protecting their health during the months-long journey. The International Mars Mission Plan proposed by Mars Society uses this approach. The Discovery one in 2001, A Space Odyssey, used a rotating section for artificial gravity, scientifically accurate, though the rapid rotation and small radius shown would create severe Coriolis effects. The Hermes in The Martian similarly rotated for gravity. The Endurance in Interstellar had a rotating ring. These designs are plausible with foreseeable technology. Rotation has other benefits. It naturally defines up and down, making spaceship layouts more intuitive. Fluids behave normally, you can pour water, and it flows downward. Bathrooms work without airflow tricks. Fire safety improves because hot air rises and cool air sinks, maintaining natural convection. These small comforts make long-duration missions more psychologically tolerable. But rotation has costs. The spacecraft becomes mechanically complex, with rotating and non-rotating sections requiring seals and couplings. Solar panels and antennas must either rotate with the spacecraft or be mounted on non-rotating hubs. Docking is harder, the spacecraft is spinning, requiring synchronization. Damage control is more difficult in a rotating structure, and any asymmetry in mass distribution causes wobbling, requiring careful balancing. An alternative to full rotation is intermittent artificial gravity. A spacecraft might spend most of its time in microgravity, then periodically spin up for several hours while the crew exercises and sleeps. This reduces structural requirements and complexity while still providing health benefits. The optimal schedule, how often, how long isn't known and would require research. Another approach is partial gravity. Mars has 0.38 grams. The Moon has 0.17 grams. Perhaps these partial gravities are sufficient for health if people aren't born and raised there. We don't know, no human has lived in partial gravity long enough to measure effects. If partial gravity is sufficient, smaller, slower rotating structures could work. Some future habitats might be built into asteroids or moons. Hollowing out an asteroid and spinning it could create artificial gravity inside. The asteroid's own mass provides radiation shielding meters of rock absorb cosmic rays better than thin spacecraft hulls. Rotating asteroids or cylindrical space stations kilometers long could house populations in the thousands or millions, creating Earth-like environments for permanent habitation. Could we generate artificial gravity without rotation? Not with known physics. If we discover how to manipulate gravitational fields directly, creating localized gravity generators might become possible. But this requires technology and understanding we don't have. Some science fiction invokes gravity plating or graviton generators that create downward force without rotation. Such devices violate known physics. They'd require controlling space-time curvature without mass, which we don't know how to do. For now, rotation remains the only practical method. And while rotating spacecraft present engineering challenges, they're challenges of scale and complexity, not fundamental physics. A rotating station or spacecraft is technically feasible, expensive, and difficult, but possible with existing materials and engineering knowledge. As we commit to longer missions farther from Earth, artificial gravity will transition from science fiction concept to engineering necessity. Beyond its effects on human spaceflight, gravity is the universe's architect. It shapes galaxies, builds stars and planets, and governs the cosmos's large-scale structure and evolution. Understanding gravity's cosmic role reveals its centrality to existence itself. Gravity built the universe's structure from tiny initial fluctuations. Just after the Big Bang, matter was almost perfectly uniform, with density varying by only 1 part in 100,000. But these tiny variations had slightly stronger gravity, attracting nearby matter. Over millions of years, denser regions attracted more matter, growing denser still. This process, gravitational instability, amplified microscopic density fluctuations into today's galaxies and clusters. Dark matter played a crucial role. Normal matter, atoms, light, everything we see, makes up only about 5% of the universe's mass. About 27% is dark matter, matter that doesn't emit light but exerts gravity. Dark matter clumped together first, creating gravitational wells into which normal matter fell, forming galaxies. Without dark matter, galaxies couldn't have formed quickly enough. The universe wouldn't look like it does. Galaxies are gravity's triumph. A galaxy contains billions of stars orbiting a common center, held together solely by gravity. The Milky Way contains 200 to 400 billion stars orbiting the galactic center. The Sun completes one orbit every 230 million years. Gravity balances the star's orbital motion, creating stable structures that persist for billions of years. At galactic centers lie supermassive black holes, millions to billions of solar masses. Nearly every large galaxy has one. These black holes don't dominate their galaxy's gravity. They're only a small fraction of the galaxy's total mass, but they profoundly influence galactic evolution. As matter falls toward the central black hole, it forms an accretion disk, heating to millions of degrees and emitting intense radiation. This radiation can blow away surrounding gas, regulating star formation. The balance between star formation and black hole feeding shapes galaxy evolution. Galaxy clusters, groups of hundreds to thousands of galaxies, are the universe's largest gravitationally bound structures. The Virgo cluster, 50 to 60 million light-years away, contains over 1,500 galaxies. Gravity holds the cluster together against the universe's expansion. Hot gas between galaxies, heated by gravitational energy as galaxies move through the cluster, glows in X-rays. Observing this gas reveals the cluster's total mass, including dark matter. Dark matter outweighs visible matter in galaxy clusters by about 6 to 1. We detect it through gravity. Galaxies in clusters move too fast to be held by visible matter alone. Dark matter provides the additional gravity needed to keep clusters bound. Similarly, stars in galaxies orbit too fast to be held by visible matter. Dark matter halos surround galaxies, providing the gravity needed for observed rotation speeds. On even larger scales, galaxies aren't randomly distributed. They form filaments and sheets separated by vast voids. This cosmic web structure emerged from gravitational collapse. Overdense regions collapsed into clusters. Underdense regions expanded into voids. The result is a foam-like structure with galaxies concentrated in walls and filaments surrounding empty voids. Gravity also builds stars. A cloud of gas in space will eventually collapse under its own gravity, fragmenting into clumps that become stars. As a clump collapses, gravitational energy converts to heat. The cloud's center heats up. Eventually, temperatures reach millions of degrees, and nuclear fusion begins. Hydrogen fuses into helium, releasing energy. The energy from fusion creates pressure that balances gravity, stabilizing the star. A star's life is a battle between gravity trying to collapse it and pressure from fusion trying to expand it. As long as fusion continues, the star remains stable. When fuel runs out, gravity wins. For Sun-like stars, the core collapses into a white dwarf. For massive stars, collapse continues past white dwarf density to neutron stars or black holes. Planets form from disks of gas and dust around young stars. Gravity pulls dust together into larger clumps. Clumps collide and merge, building ever larger objects, planetesimals, then protoplanets, then planets. Gravity shapes planetary systems, determining which planets form, where and how their orbits evolve. Gravity even affects light. Einstein's general relativity predicts that light bends near massive objects, following curved spacetime. This gravitational lensing was first observed during a 1919 solar eclipse. Stars near the Sun's edge appeared shifted from their normal positions as the Sun's gravity bent their light. Gravitational lensing is now a standard astronomical tool used to map dark matter and observe distant galaxies magnified by foreground clusters. Dark energy, discovered in the 1990s, is gravity's cosmic opponent. While gravity pulls matter together, dark energy pushes space apart. It dominates the universe's expansion, causing acceleration. Dark energy makes up about 68% of the universe's total energy, yet its nature is unknown. Is it a cosmological constant energy intrinsic to empty space, or a dynamic field that changes over time? Understanding dark energy is cosmology's biggest challenge. The universe's fate depends on the balance between gravity and dark energy. If dark energy remains constant, expansion will accelerate forever. Galaxies will recede beyond our cosmic horizon. Eventually, stars will exhaust their fuel, galaxies will dim, and the universe will become cold and dark. If dark energy strengthens, expansion could accelerate catastrophically, tearing apart galaxies, stars, planets, atoms, a big rip. If dark energy weakens, gravity might eventually overcome expansion, causing the universe to recollapse in a big crunch. Current observations favor endless accelerating expansion, a cold, dark future. But dark energy's behavior over trillions of years is uncertain. The universe is 13.8 billion years old. Its fate will play out over trillions of years. We're still early in cosmic history. Gravity isn't just a force, it's the scaffolding on which cosmic structure hangs. It built galaxies from primordial fluctuations. It powers stars and black holes. It shapes space-time itself. Without gravity, the universe would be formless, a diffuse gas expanding forever, never forming stars or galaxies or planets or life. Gravity is why the universe is interesting rather than boring, complex rather than simple, full of structure rather than empty uniformity. We began with a question: how do gravity and weightlessness work? We've journeyed through the physics of gravity from Newton's universal law to Einstein's curved space-time. We've explored weight and weightlessness, learning that astronauts float not because gravity disappears but because they're in continuous freefall. We've examined orbits, understanding them as balance between falling and forward motion. We've investigated microgravity's subtle effects, anti-gravity's absence, and artificial gravity's challenges. We've seen gravity at extremes in black holes and neutron stars, and gravity's cosmic role building the universe's structure. The central insight is that gravity is always present, always pulling, shaping space-time itself. Weightlessness isn't gravity's absence, but a special condition free fall where gravity's effects transform from force to motion. You don't feel gravity itself, you feel resistance to gravity. Remove that resistance and you float, regardless of gravity's strength. This understanding transforms our intuition. The ISS orbits in strong gravity, not zero gravity. Astronauts aren't in a special place where physics changes. They're in perpetual free fall, a state achievable anywhere in orbit, in a falling elevator, in a dive from a plane. Gravity remains, only the sensation changes. Einstein showed us that gravity isn't really a force but geometry. Mass and energy curve space-time. Objects follow those curves. This perspective unifies falling apples and orbiting planets, time dilation and black holes. It's profoundly different from Newtonian intuition, yet more accurate and complete. Yet, mysteries remain. We don't know how to reconcile gravity with quantum mechanics. We don't understand dark matter or dark energy, which dominate the universe. We can't manipulate gravity or create anti-gravity. Gravity at the Planck scale, in black hole centers, and near the Big Bang remains beyond our theoretical reach. Perhaps future discoveries will reveal new aspects of gravity. Quantum gravity might allow phenomena currently unimaginable: wormholes, warp drives, or ways to manipulate space-time directly. Or perhaps gravity's current understanding is nearly complete, and future progress will be refinement rather than revolution. For human spaceflight, gravity's challenges remain practical. Microgravity damages health. We need countermeasures or artificial gravity for long missions. We can't escape gravity's pull. Cheaply reaching orbit requires enormous energy. Journeying to other worlds means battling gravity wells repeatedly. These aren't insurmountable, but they're expensive and difficult. Yet gravity also enables space exploration. Orbits provide stable platforms for satellites and stations. Gravitational assists let us explore distant planets without massive fuel loads. Planets themselves, gravity-bound concentrations of resources, are destinations for settlement. Gravity, while challenging, is also infrastructure. The story of gravity is humanity's long journey to understand nature's most pervasive force. From Aristotle's natural place, to Newton's universal law, to Einstein's curved space-time, to modern searches for quantum gravity, each generation refined understanding. We're not at the end. Quantum gravity remains elusive, dark energy mysterious, gravity's relationship to other forces unclear. But we've come far. We can predict planetary orbits centuries ahead, detect gravity waves from the universe's edge, navigate spacecraft through the solar system, and keep astronauts safe in orbit. We understand falling and floating, weight and weightlessness, orbits and escape. This knowledge isn't just abstract, it's practical, enabling the space age. As you drift towards sleep, reflect on gravity's omnipresence. It's pulling you now, as always, toward Earth's center. The ground pushes back, creating weight. But imagine the sensation removed: free fall, weightlessness, floating. Astronauts experience this daily, a reminder that familiar sensations depend on context, not just physics. Gravity connects you to the cosmos. The same force pulling you down pulled together the gas cloud that became the sun and planets. It holds the moon in orbit and the planets around the Sunday. It built galaxies and will determine the universe's fate. You're part of this gravitational tapestry, connected by invisible threads to everything. Tomorrow, gravity will still pull you down. Astronauts will still float overhead. Planets will still orbit the Sunday. The universe will still expand. Gravity and dark energy in eternal tension. These certainties persist, governed by laws refined over centuries of observation and thought. Rest well, knowing that gravity, mysterious as it remains, is understood well enough to send humans safely into space, predict cosmic events billions of years hence, and reveal nature's deepest workings. The force that keeps you grounded is the same that shapes galaxies. You're subject to nature's most fundamental architecture, the curvature of space-time itself. Sweet dreams, fellow traveler. May your rest be as deep as a gravitational well, as peaceful as an orbit, as effortless as floating in free fall. The universe pulls at you with invisible strings, but tonight, release into sleep's microgravity, where weight and worry fade, leaving only the gentle drift toward dreams.